excuse me, from last year. So let's take a look at this here. And over the next few days here, that's what I plan on doing with you guys, is working through a little bit of review. Freshman is one of those 10 topics where ideally your eighth graders, your eighth grade teachers talk to this about you. How much did it stick? I don't know. Just kind of depends, again, how much your eighth grade teachers did with you on it. So we'll just go through there, and I have some problems in there that are kind of more geared towards SAT style questions as well. All right, so let's do that, and then each day I've got something new with it. We're gonna move this kind of quickly on things, and yeah, each day is something a little bit new. We're gonna do by graphing today, and then when we can't graph, we're gonna do the substitution method tomorrow. And then on Thursday, Friday, we're going to do another method we call the elimination method, as you might have remembered. And then next week, we're going to do what we call as linear inequalities. And that's pretty much where our time will kind of leave us. And sophomores, you'll be testing. Freshmen will do a little bit more work, because I'll have you at least for another day or so. And then that'll be about it. And then after that, we'll talk about our last round of geometry. Okay? Now, let's do this. Let's go ahead and take a look at one of our first questions here. SAT, one of the very first things they do is kind of sometimes give you almost like a free question. What's the solution here? When we talk about a system is more than one equation, all right? When you have more than one equation, we call that a system. And in this instance, to start off with, we have two graphs there. It's more than one equation that's there. We have two lines that are intersecting, and what we want to know is what's the solution. Where they intersect is the solution to that system. So where does those two systems, or where do those two lines, where do those two lines intersect at? What's this location? What's location? Yep, 1, 2. So where the intersection is the solution to that system. So as you just told me, 1, 2. Okay, is the solution to that system. Okay. Now, questions that again SAT like to kind of go back and keep asking you is about knowing your quadrants, knowing your axes. So follow-up question to that is, what quadrant are we located in? What's the solution located in? Quadrant what? 1. That is quadrant 1. Okay. Our quadrant 1 is up here in the top right. As we've again talked about that randomly throughout that school year. Quadrant 1, and where's my quadrant 2 located at? Quadrant 2 is located where? To the what? Left? Quadrant. Maybe a little better there. Quadrant 2 and quadrant 3 and quadrant 4. Okay? So we are in quadrant 1. All right? Now, there's my SAT practice with you on the next question. This is usually what question that SAT will ask you. So let's take a look at question 2 with it. If xy is the solution to the system of equations graph below, what is the value of, say, 3y? All right, so we got to again know how SAT asks style of questions. When we look at this one here, well, what is the intersection there of those two lines? What's the intersection? -1, -2. So we write that off to the side, but that's not how SAT is wanting us to answer the question. What is the value of 3y? When you just identified that location there, what value is y, and then what is the value of 3y? So which of those two coordinates is y? The -1 or the -2? -2, right? The x comma y, that is the y. So when we say y, 3y is 3 times, because that's times, and 3 times -2, then you're going to say, or select, whatever answer is -6. Okay, so that's what the SAT likes to do for you, is ask you a question like that, where they go one more step. Not just necessarily what's the ordered pair, but what is this last part right here? What is the value of 3y? What's the value of 2x? What's the value of x plus 5? That's what SAT likes to do. Now, usually these are also tied to questions that are the grid response, the bubbling type of questions. So those grid response ones that we've been doing throughout the year, Make sure that you are bubbling those in correctly. Now, one more thing though, can we bubble in a negative on those, if you remember? Can we bubble in a negative? No. Those are only positives that we can do. Now, we cannot bubble in a -6, all right, because we can't bubble in negatives. You can only bubble in positives or fractions, okay? So just small things to remind yourselves on. And where is our intersection located? That is located in quadrant what? Quadrant 3, isn't it? Okay. So that's some of our SAT practice. Usually there's about one of those a year on there. There are definitely some patterns that if you look from the SAT 9th grade, 10th grade, and the 11th grade, there's usually some patterns that the SAT usually always has every year. Those tend to be some. Last week I've been throwing out those function type questions. I would put money on for sure you guys having at least one of those style of questions on there. Probably going to have a system R2 on there as well like that. All right, let's take away already graph ones and you go do letter A. Graph me out those two equations there. See where the intersection is located. Okay, so take letter A then, go graph me out those two lines. And where is the intersection located on that first one there? Okay, so graph me those two lines and again, find me the intersection. Y equals what? 2x plus 1 and y equals 3x minus 1. Where is the intersection located? And when you are graphing like this, if you are not landing at a nice intersection, a nice point, then you've done something wrong. I will not give you a point that is not at a nice location. It's got to be a nice integer location. -1, 5, 2, 3. But if you're getting at like a 1/2, 3, then you've done something wrong. It's going to be at a nice location that you can definitely tell. We always grab the y-intercept first, and then we play that slope game, right? And we've done plenty of review of lines throughout this school year, and then up to right 1, don't we? And then this is where we always talk about my Algebra 1 kids, as we've done probably more graphing of lines than you guys have throughout this school year. I always like to give a few more points than just say 2 points to make a line. Up to right 1 is the same thing as going down 2 and left 1. A few more points, just make a better line. Take your ID, make a line, try to make a better line than I just did. And then on that second one, same deal. And this is where, again, making a few extra points like this will make a better line, because those extra points that we just did to make that line, when you make that second line, I almost guarantee you, on that second line, you're going to run into the one of those points that you just previously made. So -1 starts it, and then what is it? Up 3, right 1. Up 3, 1, 2, 3, right 1. 1, 2, 3, and there we go. And as soon as you run into that point on the other line, you can stop and make that line. If you didn't run into it, then reverse it. Go down 3, left 1. Now you're not going to run into it, but once you run into it, call it a day. And then tell us the intersection then. Okay, what is my intersection located at? What is that? 2, 1, 2, 3, 4. Is that 5? 2, 5. Okay. Nothing crazy going off of that. All right. Take letter B. If you haven't done so yet, go do letter B real quick. On letter B, watch that negative slope on that top line. Nothing crazy again with that, but watch that top line with that negative slope. Okay. And hopefully this is, again, if it hasn't done so yet, starts jogging your memories already on there. Okay. got down one, right one. So your eyes on that one, once you make that graph, should be going down because it's a decreasing slope. And that's that first one. And then for the other one, your eyes should be going up because the slope is positive. And what do we got? Up 3, 1, 2, 3, right 2, and then down 3, 1, 2, if I can count. 1, 2, 3, and then left 2, and there it is right there. Hits that graph. Take your ID and make the line. And what's that nice location? -2, -1. Always check your work, check my work, and call it a day. Okay. So flip it. Let's go to the next page. Nothing crazy off that, but you got to make sure you are in slope-intercept form. So as we see the next page, that second one is not in slope-intercept form. So let's bring in our rearrangement skills on that second one. Top one's good to go, but that bottom one is not in slope-intercept form. So quickly graph that top one, but that second one, you do need to rearrange it, get it into y equals mx plus b for yourself. But that top one's good. That top one, go ahead and graph it really quick. Get that out of the way. We know how to graph y equals 2x minus 3, no big deal there. But it's that second one that we need to go ahead and rearrange and solve for y. Again, use all your equation skills that we've used throughout this semester, throughout the year, and since you guys have been doing since 6th grade as well. That bottom one, that top one, get that one out of the way real quick. And then up, what is it, 2, right 1. Up 2, right 1. Up 2, right 1. Up 2, right 1. Down 2, left 1. But now it's that bottom one where we want to make sure you are rearranging that bottom one correctly. Getting into y equals mx plus b, getting into slope-intercept form. Okay. So getting into slope-intercept form, y equals, again, mx plus b. Got to get rid of that 3x first. Then we got to get rid of that 3 in front of the y. So it's a 3y minus 3x. Getting that -3x, kicking it to the other side, do your inverse operations. Just like you solve for y, get rid of that minus 3x. Add that 3x to both sides. And then divide both sides by 3, right? It's attached by multiplication, and the inverse multiplication is good old division, and make sure you divide everything by 3. So what we're actually graphing is y equals x minus 1. Okay? So if you're not in slope-intercept form, get it in slope-intercept form. Okay? And then graph it again and see where they intersect at. So these are usually nice to go, but if we're not in slope-intercept form, get it in slope-intercept form. So down 1, start it off with at the y-intercept, and then play that slope game of up 1, right 1, up 1, right 1. Again, you should not have to think anything of this. These are your 6th through 8th grade through Algebra 1 prior knowledge skills. And what's my intersection there? What is that, 2, 1 looks like? 2, 1. All right. Now, what I always like to do with everybody then is, intersections are solutions. Where things intersect at are solutions. I don't care if it's 2 lines intersecting. I don't care if I have a quadratic up there. On the next one, I give you a parabola already graphed. So what I have is a quadratic. Go graph the line on the next one. You know how to graph a line. We do not know how to graph a quadratic yet. We had the time, which we don't. Okay? We would talk about learning how to graph a quadratic. That's an Algebra 1 skill. But we just don't have the time there. Next year in Algebra 2, that's one of the first things you guys will go off with. They're going to take you. You already know how to factor. They're going to continue on with those skills and build off your factoring skills and then on a couple other things. And factoring, going from factoring to graphing quadratics is what we'll do with you. But I gave you a graph. Go graph the line. And Where things intersect at, those are solutions. So you guys can graph a line, no big deal. Go graph that line and show me where things intersect at. And again, where things intersect, if it's two lines, if it's a line and a quadratic, if it's two quadratics, if it's a line in a circle, if it's a quadratic in a circle, I don't care. It's two circles. Whatever. It's an absolute value in a line. Where things intersect at, those are solutions to a system. I want you to think about, again, big picture ideas. Where things intersect at, those are solutions. So where does this intersect at? Go down one, play that slope game of what? Up one, right one, right? And just keep graphing a line. And then as we keep graphing a line going down one, right one, what do we got for our solution, everybody? Where's my solution located at? Okay, what I heard 1, 0, right? 1, 0, and anything else? So this is an example of where we've got ourselves two solutions. Now, in the lines that we've just been doing, to start off with two linear equations, the best you can do is a solution. There's no way you can take your arms and get more than a solution. There's two lines, can't break your arms, all right? You can only get yourself what? A solution. But once we get ourselves a parabola going, or once you get your arms going there, but your U-shaped graph, your parabola here, we can get ourselves two solutions. If it's V-shaped graph for an absolute value, we talked about some absolute values last week as we did some function work. Okay, same thing, we can get two solutions. Now, let's add on to this here real quick. What if I didn't have a V-shaped graph, or sorry, a line like that? What if I gave you a different equation that was, how many solutions would I get if I graphed a line and it turned out to be like this? How many solutions do I have here? No solutions. So I can get a one solution. I just saw two solutions, but if the line never intersects, I get no solutions. How could I get a, whoops, wrong button. How can I get a one solution? Hey. Big folder. Yeah. All right, thanks, Ray. Or not Ray, but you're Gracie, that's for Ray. See you later, Grace. All right, what if I got this one? Excuse me. How many solutions do I got here? One solution. This is a tangent because how many points is it coming in at? It's just one solution is coming, just touching it and moving on, right? It's tangent to this parabola.
What if you have two of the same line? What do you say?
Two of the same line, like a line and then one right on top of it.
Yeah,
we're gonna see it in a second, I think, right?
Yeah.
Yep. Give me 1 second there, and that one we're gonna see in literally just a second. No, we will. Okay. So we get one solution back to one solution. So don't overthink those types of things. So let's go and do that, because that's happening on down here in a second. Let's go graph number 4, letter A, real quick. Go graph out letter A. And what we just saw then on those last couple then are some special cases. So as you graph number 4, letter A, you graph those, they seem like, again, probably normal ones. Not saying normal ones, but they seem just general, regular old linear equations. You graph out that top one, y equals 2x minus 1, and the y-intercept starts off at -1, bless him. The slope is 2 over 1, so up 2, right 1, up 2, right 1, down 2, right 1, sorry, down 2, left 1, down 2, left 1, take your ID, make the line, and we go to the next one, and we do the same thing. Y-intercept is not at -1 this time, the y-intercept is at 0, and then we play that slope game all over again. And what we're looking for is these two lines to intersect. Up 2, right 1, up 2, right 1, up 2, right 1, and down 2, left 1, down 2, left 1. And are these two lines, again, as many times as you keep doing that, are they ever going to intersect? No. And what do we say then here? Correct. Now, as my Algebra 1 kids took that test a few weeks ago, there's shortcuts off of this. Instead of graphing these lines, let's generalize this out. How do I know these things were never going to intersect? As we look at these solutions, or sorry, we look at these equations, we look at the system as a whole, what tells me that up here that they're not doing? And we talked about this at the very beginning of the school year as well. The slopes. Now, it's not just the slopes. It's the same slope, but it also has to look at what's true about the y-intercepts. Or what's true about the y-intercepts here. Correct. Same slope and a different, you got to look at the whole thing. You got to look at both pieces. Because the slopes are different, the slopes are the same, the y-intercepts are different. If the y-intercepts are the same, we get a different result, which is the next one. So if you don't haven't done the last one there, letter B, let's go do it. Okay. Go grab the next one real quick.
Let me see you draw. Share with the class.
I shared it around. Okay, I'll walk around in a second here. Let's finish these off. Alright, we graphed that top one. Alright, Blake, I'll get to you in a second then. So when we go graph this next one here, y-intercept is 2. Slope is what? -3. So what's that? Negative. Down 3. So 1, 2, 3. Right 1. So down 3, right 1. Give me a few points off of that. Mr. Josh. Yes. Yes. All right. Down 3, right 1. Down 3, right 1. 1, 2, 3. 1, 2, 3. Reverse it. Up 3, left 1. Take your ID. Make the line. Blah, blah, blah. Okay. Then on that second one, okay. Then on that second one, same thing's happening where it's not in slope intercept form. So with that not being in slope intercept form, we need to again go through and put that, divide by 2, and put that into, again, slope intercept form real quick. So go ahead and do that if you haven't done so yet, as I write out this. All right, I don't. And as we divide that by 2, what we end up with then is the same equation. Now playing dumb here, which is not much of a play. Okay, as I play that y-intercept and I go down 3, right 1, down 3, right 1, and up 3, left 1, again I realize I'm graphing the exact same line. And it's not a no solution, it's not a one solution. What do we say here? Anybody remember? Or you could also say, yeah, either one is fine. Infinitely many solutions. So any ordered pair that you can pick on this line here is a solution to that. Or as you also just said, all real numbers. Either one of those can be used interchangeably as writing up as a solution off that. Now, again, shortcuts. We're all about shortcuts there. What was the distinguishing factor from this one to that last one? Slopes are the same, but that didn't give me a no solution off that. What was the distinguishing factor there? Same slope, but what finishes it off? The y-intercepts are the same, okay? You have to look at both pieces, not just the slope. You gotta also look at the y-intercept. Thank you. So really quick down below, let's play the knockout game. All right, got another one. Alrighty. So, right across the board, quick rapid response, looking at those slopes and y-intercepts. What do we got? One, no, or infinite? Infinite. Same y-intercept, same slope, same y-intercept. This is infinite right here, okay? Those are those, again, quick responses you should see as a whole. Don't even need to graph these. Number 6 there. What do we have on that one? You said no solution? Should be a no solution. Same slope, but the y-intercepts are different. What that means is we're going to be parallel, and parallel lines do not intersect. This gets me a single line, that's infinites. And then the last one, what's the slopes doing there? The slopes are different. And as soon as the slopes are different, I'm done. It's going to intersect, and intersecting means we get a single solution. Okay, I don't care about the y-intercepts. Y-intercepts can be the same. They don't have to be the same, but the slopes are different. That's what we just did on the other page to start off with today on. They intersect some way somehow. So look at those slopes to start off with. All right, and then look at the y-intercept to finish it off. Okay. All right. Let me pass out the assignment here today.